All right, 7 o'clock, so let's go and get started. All right, good evening, everyone. Good evening, everyone. For the second to last time this semester, how's everyone doing today? Good, good. All right. So we're in the last week, and so for most of this week, we're going to be working on just the project, and so we have our project workshop. But I did want to talk about the Neumann boundary conditions because we didn't get to that last week, right? And so remember from last week, we wrote the code together for the example that we did, And so that should help you out with parts 1 and 2 of the project. But I wanted to make sure I talk about the Neumann boundary conditions a bit this week, mostly today. So it'll probably take about, maybe 20, 30 minutes, just so that you kind of know how to get started on that part of the project for part 3. And then from there, I'll just kind of open it up. And so, if you want me, so we'll just have kind of free project working time. And so, if you want me to look at your code, I can definitely do that. So just going to raise your hand and I'll come over. But if you're on Zoom, just drop a message in the chat and then I'll come help you out from there. Okay. Okay. And so, are there any questions on anything before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. Okay. And so this is Neumann boundary conditions with isoparametric elements. Okay. So this is the last thing that we have to do in order to kind of complete our isoparametric approach or isoparametric concept. Okay. And so it's this idea that, if you have an element, right? So obviously this is an element in the physical space because the element is kind of wonkily, oriented. Okay. And then on this element, this element straddles a border of your domain. And so, I'm going to go ahead and draw a line right here. Okay. And so that line right there represents the actual border of your domain. So not just the element, but of the entire domain. Okay. And this domain, or this border of the domain, just happens to be a location where you're applying a Neumann boundary condition. Okay. So remember, Neumann boundary conditions, those are things like our stress, our applied loads, stresses, if we're talking structural mechanics. But for heat transfer phenomenon, this is where we're applying our heat flux boundary conditions. Okay. And so what we need to do is we need to apply this Neumann boundary condition on this element. Okay. And what it's going to do is that it's going to alter the value, alter the values of the element forcing vectors. Okay. Okay, and of course that's FE. Okay. All right. And so of course, since this is an isoparametric element, we're gonna perform the Neumann integral using Gauss Quadrature. Okay. But we have to perform it in a really kind of special way. Because remember, the Neumann boundary integral is only a 1D integral, right? But our shape functions for 2D elements like this have two degrees of freedom. Okay. And so if our shape functions are 2D, but we're only integrating out one of the variables, that means we have to do something with the other variable. And so that other variable that we're going to do, what we're going to do is we're going to hold it fixed at a certain value. Okay. And so I'll give you an example. And so this is the example that we're going to work out by hand as well. Okay. And so for this particular element right here, okay, this element is in the physical space. Okay, so this is our element that's in our mesh. And so remember, the first thing we're going to do is we're going to take this element in the physical space and map it to the parametric space, right? And so we're going to have a nice uniform element here in the parametric space. Right, so that's the first thing that we do when we perform isoparametric elements, is perform this mapping. Okay. And then after we perform the mapping, we have to pay attention to, which edge on this parametric space is our boundary condition being applied to. Okay. Okay. I say edge is plural because it is possible for you to apply Neumann boundary conditions to more than one edge. That's not going to be the case for your projects, but just kind of keep that in mind, that you might have to repeat this process for maybe two edges, maybe three, in some cases, but usually at least one, but sometimes two as well. Okay. And so in this particular example here, we have our Neumann boundary condition applied on the top edge. Okay. And so what we know about the top edge is that it runs from left to right, right? It runs from left to right. And then as we travel along that edge, right? And so in other words, as we perform this integral along that edge, we can see that we have one coordinate here that's going to be fixed. And the one coordinate that's going to be fixed is our eta value. Okay. Okay. And so that gives us a hint about how we're going to perform our integral, right? Because normally our integral looks like the following, right? And so our Neumann boundary integral our Neumann boundary condition integral looks like the following. And so we have integral from -1 to 1, okay, of our shape functions. And so this is our four shape functions. Actually, let me draw it out as such. Okay. So we have n1, n2, n3, and 4. Okay. We're going to multiply this by our Neumann value. Okay, so that's like our prescribed heat flux. Okay. We're going to assume that we already applied our change of coordinates, and so what we have right here is the Gaussian, or not the Gaussian, the Jacobian. Okay, and the Jacobian for a 1D integral member is just simply the length, the original length of the edge, divided by 2. Okay. Okay, so this L right here is length. Okay. L right there is the length of the physical edge, and so that's our Jacobian. Okay. And then we're integrating this over ds. Okay. And I'll define s in a second. But our result from this is basically, because our shape functions here is a is a 4 by 1 vector. Okay. So that's going to be the result of this integral here. We're going to take that 4 by 1 vector and add it directly to our element forcing vector. Okay. And so if you break apart this integral, a lot of it's actually, pretty easy, right? First of all, I'll talk about the shape function in a second, but the first thing that we see is that we have our Neumann value, right? And so this is usually given to us, or it's some fixed value. Okay. Okay. So that's usually not an issue, because that's normally defined at the very beginning of your simulation. The next thing that we have is the length of the physical edge. So I will say that this might be going to be a little bit tricky to do in the project, but but conceptually speaking, it's not that bad. Okay. Right. It's tricky, but it's not going to be the trickiest part of part 3. The trickiest part of part 3 of the project is what you're going to do with the shape functions. Okay. And so I kind of left a space here on purpose. Okay. Because normally these shape functions are functions of both epsilon and eta, correct? Right. They're functions of those two values. But remember, when we perform this integral here, this is only a one-dimensional integral. And so one of these values we're going to have to keep fixed. And which one we keep fixed, or how we fix it, is totally dependent on which edge that we're talking about here. Okay, so it's very edge dependent. And so for this particular case, where our Neumann boundary condition is on the top, we're going to fix eta to 1. Okay. Okay. And so that means that the integration variable, or the variable that we left open, that's what we're going to integrate over. Right, so the most generic form of this integral here is the integration variable is I just called S, but that's either going to be epsilon or it's going to be eta, depending on which edge that you're on. And for the triangles, there's actually an added more complication too, where if you're integrating on the diagonal, then it's not really quite fixed one or the other. But we'll kind of cross that bridge when we get there. Okay. Okay. All right, so that's the idea. That's the idea with Neumann boundary conditions. So if I had to sum this up, okay. First thing you have to determine is, first of all, you have to determine if there's a Neumann boundary condition on this element at all. Okay. Because for the majority of elements, you're not going to have a Neumann boundary condition applied onto it unless you have a lot of loading for some reason. Okay. Number 2, once you've determined that if there is a Neumann boundary condition on this element, you have to determine which edge or which edges the Neumann boundary condition is being applied on in the parametric space. Okay. Okay. once you determine which edge that you're going to apply the boundary condition on, you need to determine, which coordinate is going to be fixed and which coordinate you're going to integrate over. Okay. Okay. Or, so those first two questions will cover the rectangle just fine. But for the triangle, there's an added complication where you might be integrating over the hypotenuse of the triangle. Okay. You might have a third situation where neither one is fixed, but they have a relationship together. Okay. And I'll explain what that means later. Okay. All right, so once you determine those things, number 4 is to perform your 1D Gauss quadrature. Okay. So you're going to perform that 1D Gauss quadrature. And once you've done that, then you're going to end up with that 4y1 vector. And you're going to add this contribution to the element forcing vector for that element. Okay. Okay. Right. So in general, that's kind of the 5-step process that you're going to have to go through for these Neumann boundary conditions. Okay. Any questions on this before we do a quick example with the problem we were looking at last week? Okay. Right. So let's look at the problem that we we're doing last week. I'm not going to do the whole thing, but let me just go ahead and draw the relevant parts. Okay. So here we have our trapezoid. Node 1, 2, 3, 4. Okay. And for this one, we have that Neumann boundary condition actually on this top edge right here. Okay. And this has a value, the heat flux out equal to 5 watts per meter square. Okay. All right, and the other thing we're going to need for this problem are the coordinates. And so the coordinates for node 1 are 0, 0. Coordinates for node 2 are 1, 0.2. For node 3, it's 0.8, 1, and 4 are 0.2, 0.1. Okay. Okay. So let's kind of run through our logic for this element or 5-step logic to determine what's the contributions to the to the Neumann boundary condition. Okay. Okay. All right. So let's look at step 1. So step 1, is there a Neumann boundary condition on this element? Yes, because we're doing the example. So of course there's a Neumann boundary condition in this element. Okay. Number 2, which edge in the parametric space is this being applied to? Okay. And so it's being applied to the top edge. And so if we map this to the parametric space, okay, which is our epsilon eta element, it's going to be on the top edge. Okay, so we have a Neumann boundary condition on the top edge of our parametric space. Okay. Step 3, which coordinate is fixed? And so since we're on the top edge, that means eta is going to be fixed at 1. Okay. Right. Step 4. Step 4, we're going to perform our Gauss quadrature. Okay, so let's go ahead and do that. Okay. And so let me just go ahead and remind you of the integral that we're evaluating. Okay. And so our integral is integral from -1 to 1 of n1 of epsilon, eta is equal to 1, n2 of epsilon, eta equal to 1, and 3 of epsilon, eta equal to 1, and 4 of epsilon, eta equal to 1. Okay. This is equal to the Neumann boundary condition value, which is given to us, as well as the length of the edge divided by 2. And in this case, we're integrating over epsilon. Okay. So I'm just checking something real quick. Okay. And so we have Q out, and so Q out is given to us in the problem is 5. Okay. Let's compute before we do the Gauss quadrature. Let's compute the length. Okay. All right, and so the length is going to be the length of the connecting edge between nodes 3 and 4, right? And so what we're going to use is we're going to use distance formula. Right? Because we have the nodal coordinates for nodes 3 and 4, and so we can just use distance formula to find the distance between them. Okay? All right. And so the length here is going to be square root x4 minus x3 quantity squared plus y4 minus y3 quantity squared. Okay. And so we have all these values here from the nodal coordinates up above. And so we plug this in, we get a length of 0.6083. Okay. And so we can go ahead and plug this in for L right there. Okay. All right. So now we have Q out. Now that we have the length, last thing to do is to apply our Gauss quadrature for this guy. Okay. And for this integral, we're going to apply a two-point Gauss quadrature in 1D. Okay. All right. And so if we plug in all the values for this, we plug in 5, we plug in that length, then we end up with a coefficient out in front of 1.52. Okay. And then we're going to apply a two-point Gauss quadrature rule. And so, for our 2 points, epsilon 1 here is going to be minus 1 over root 3. Epsilon 2 is going to be 1 over root 3. Okay. And so we're going to evaluate our shape functions, or in other words, our integrand at these 2 points. Okay. So we have two evaluations here. Okay. So I'm going to do n1, n2, n3, and 4. Oh, and the weights, of course, the weights for this are going to equal to 1. Okay. All right, so we're going to take all of our shape functions here, evaluated at the first Gauss point. And so the first Gauss point is minus 1 over root 3. Eta is still equal to 1. Okay, and that's going to apply to all 4 of our shape functions. Okay. And to this, we're going to add all our shape functions again, but evaluated at epsilon is equal to positive 1/3. Okay, so we have n1 and 2 and 3 and 4. Okay. And so I'm not going to show you all 4 shape functions again and it all plugged in. You guys can do that on your own. Okay. But I will show you the result. Okay. And because I want to show you the result because I want you guys to build up some intuition behind this. Okay. And so if you plug in all these Gauss point values and you add them up, you're going to end up with the following 4x1 vector. Okay. Okay. And so the 4x1 vector that you're gonna end up with is 0, 0, 1, 1. Okay. Where I'll kind of remind you that this first slot here is kind of like node 1's representation. Then the second slot is node 2, third slot is node 3, fourth slot is node 4. Okay. And so you notice that the only entries where we have a non-zero entry, or in fact it has a value of 1, is nodes 3 and 4, right? Nodes 3 and 4 were special on this particular element. So I could scroll up a little bit and I can label these nodes as well. Okay. Nodes 3 and 4 were special for this Neumann boundary condition because those were the nodes. In between those nodes was where the Neumann boundary condition was applied. Okay. And so you'll see this in your project too. And so what you'll see is that depending on which edge of the triangle that you're applying the boundary condition on, the 2 nodes that straddle that edge, they're going to have your non-zero entry. So that's going to be 1. Okay. So that's a good sanity check that you can do to check your work to see if your code is working out properly. Is check and see, which entries of your Gauss Quadrature integral are non-zero, and those should correspond to the nodes that straddle the Neumann boundary condition. Okay. And so our last step here is just to perform this multiplication. And so we perform this multiplication, we get 0, 0, 1.52, 1.52. Okay. And so we can take this result here and add it to FE. Any questions on what we did for this example here? Okay, all right. So before I let you guys loose for working on the project, I do want to show you part 3, or at least the starter code for part 3, just so you can relate it to kind of what we did here. Because the way we implemented MATLAB, it might look really different, but you'll see that we follow kind of the same conceptual steps. It's just that the way that you implement it is a bit different. Because we're working with arbitrary elements, right? So we're not working with, with kind of a nice element like this. Okay, so let me go ahead and share my screen. Okay, so this is part 3, the starter code for part 3. And so if you're at this point of the project, then that's great. I think you're in great shape if you're at this part here. Okay, and so here is where you insert your code from part 1. Here's where you insert code from part 2. Okay. And so here is the kind of the big addition to the code in part 3. Okay, and so in this part, just like the title says, you're going to apply the Neumann boundary conditions. Okay, and so if you look back to our notes, you're going to see we follow kind of all 5 steps of the process in this code. Okay, and so first thing we need to check, and so first thing we check to see is that do we have a Neumann boundary condition on this element? Okay. And so the way that we're going to check that is we're going to use these 2 functions here. Okay. First of all, the way that we specify the Neumann boundary conditions is we number the edges, right? And so just like that, just like the way you apply the Dirichlet boundary conditions, you're going to specify which edges in your mesh that you're going to apply the Neumann boundary condition. Okay. And so just kind of automatically, just kind of by the way that we are implementing this, we're only going to visit the elements that border this boundary. So that's kind of automatically satisfied. Okay. And so the first thing we're going to do is we're going to use this find nodes function. And so what this will do is this will find all of the nodes that sit on that edge. Okay. And we're going to use this find elements function to find all the elements that are attached to that edge as well. Okay. And so if you notice, I call these two variables Neu nodes and Neu elements. Okay. And so these two data structures here, these two vectors, they're going to show you, all the nodes that are attached to this, all the nodes that are attached to this edge, as well as all the elements that are attached to this edge. Okay. Next thing you're going to do is you're going to get the Neumann boundary condition value for this edge. And so, this is a simple one line code. And so you're going to basically make use of this entry right here. Okay. And so if you've already implemented the Dirichlet boundary condition, that should be pretty obvious. Okay. Okay. And so the next thing that you're going to have to do is in this loop. And so this loop, I think will be the loop that a lot of people will struggle with. Okay, but I've kind of broken down the steps for you here. Okay, so first thing you have to do is you have to compute the nodal ID numbers. Okay, so that's going to be your IND1, IND2, IND3. Okay, so if you've done part 1, part 2, you should be familiar with this. And with this, you're going to use connectivity in some way. Okay. Okay. And so here's where things get a little bit confusing. Okay, and so our elements in this part or in this project are triangle elements. Okay, right, so they look something like this. And so if you have a Neumann boundary condition on this element, right, then it might look something like this. Okay. And so what you're going to need to determine is, between which nodes is this Neumann boundary condition being applied to? Because it can be applied on these two, it can be applied between these two, or these two, right? And so you're going to need to determine which one that is. Okay. And I've kind of written one section of the code already for you, right? And so this this entry right here, this is kind of like a template for how you can do the other ones. Okay. So basically what we're checking is we're using this function in MATLAB called isMember. And what we're checking to see is that if N1, so N1 being IND1 up here, okay, so actually let me go ahead and fix that. So this is IND1. Okay. If IND1, or if the nodal ID is part of this set of nodes here that are sitting on that edge, then we're going to mark it. Okay. And so the way that we mark it is that we have this vector right here called boundary nodes. And if that node is sitting on the edge, then we're going to set that equal to 1. Okay. And so ideally, by the time that you reach this part of the code, okay, two entries of the boundary node vector should be activated. Okay, because you should be able to find 2 nodes that are sitting on that boundary. Okay, but you might have some instances because we're making an arbitrary mesh, and so let's say that this is a boundary right here. Okay, you might have some instances where you have an element that looks like this. Okay, right. And so for this case, this element, it's true that this element is sitting on the Neumann boundary, but it only has a single node on it. So it doesn't have 2 nodes on it, right? So to compare that to maybe a neighboring element that looks like this, right? And so element smiley face here has 2 nodes on the edge, right? Or on the boundary. And so you should be able to find 2 nodes here that are straddling that boundary. Whereas for element frowny face, right? This one only has a single node that's on that boundary. And so we want to avoid trying to perform integrals on this element because it only has a single node. And so when you're applying your Neumann boundary conditions, you can only apply it on elements that have a full edge on the Neumann boundary. Okay, so you can't apply it on elements that have only a single node. Okay, and so we need to check for that here. And so that's what this if statement does. And so what this if statement does is that, if we have at least 2 activated entries, right? And so if we sum up all the entries of boundary nodes and it is equal to 2, then we're in good shape. And so then we can actually start to apply Gauss quadrature. Okay? If the sum of boundary nodes is only equal to 1, then we don't want to do anything because we don't have a full edge there. And so we just kind of move on to the next step. Okay. Okay. And so from here, the next thing that we're going to do is we're going to get the coordinates of all 3 nodes. Okay. And so this is going to be like an x1, x2, x3, y1, y2, y3. Okay. So, we've already gone over how to go over this, how to compute these. Okay. And then the next part is going to be step 3 of our Neumann boundary condition process to determine, which coordinate needs to be fixed, or if there's a relationship between the two entries. Okay, and so that's what this part of the code does right here. And I believe I kind of explained this in the project specifications. Okay, and so basically, it checks to see, which of the boundary nodes are activated, and from there you can compute the length, and then you can specify the Gauss points for that edge. Okay. Okay, so once you've determined what the Gauss points are and the edge length, from there you just apply your Gauss quadrature. Okay. And so from here, I kind of tell you what to do, and then once you perform the Gauss quadrature, then you finally add this contribution to the element forcing vector for this element. Okay. All right, and so that kind of explains a little bit of the logic behind this this part of the code, right? It's still going to be a little bit tricky, and so I think you might have to try this a few times, but that's kind of the general idea. And so you have kind of the general Neumann boundary condition process that we just went over just now, and here's kind of the logic of how this is applied in the code. Okay. All right. Any questions on this stuff here? Okay, all right, and so from here, I'll go ahead and let you guys go. And so, you guys can go ahead and work on the project. And so we have about, how much, about 35 minutes left in the class? Yeah, about 35 minutes left in the class. And so, go ahead and work on the codes. And if you have any questions on the code, you're struggling with anything, just let me know. I'll come by and I can, I can give you some feedback. If you're on Zoom, you can just go ahead and drop a message in the chat. And then you can go ahead and share your screen and I can help you out from there. Okay. And if you haven't had a chance yet, I brought the midterm exams, and so you can come pick it up here. And yeah, and so we're going to go have and just have kind of project work time from here until the end of class. Okay. Yeah, no problem. The class isn't over yet though. Unless you're heading out, then. Oh wow! Okay. Oh great! Awesome. Well, thanks for being a great student again. Have a great summer. Okay. So you need to do. So let's look at your problem. Let's look at the percent. Is this within the? This one works. Because right now, because anything else now. Okay, because so if you go back to the start of code, and I should have caught this earlier because this KLM, you're taking the first and second, basically, you're taking 3 by 3. But ideally, this elements distance matrix should be different servers in which we factor in this ID. We'll call it 1, comma. Right, and so basically, because you're looping over all the elements, so that's what the for loop represents. And so you want to get the element stiffness matrix for that. If you look at the structure of the data structure, you get 3 by 3 for the first 2. Right, so that tells you that the third entry there. And so you're going to use that same structure for the element forcing. The element forcing vector, that would be good. No. The only forcing that you have is the okay. Part two, you're going to do the same thing. Oh, okay. Yeah, so the FE here is you're just going to have to swap this, right? So FE is going to have a similar structure. You have 1, 2, 3. Yeah, definitely. This is 3 by 5. I should go in the second. The first one should be 1. This one should be 1. This one should be 2. Should be 2. What do you guys want? Assuming you did the so looks like there's an issue with how the executed, but the assembly should be fine. So double check your code and see how. Just kind of double check with the reference code that we wrote last week, and just kind of make sure that you're kind of doing stuff. Keeping in mind that this is sort of complicated. So all right. Yeah. Yep. You good? Yeah, you good? Yeah. So yeah, if you combine it, you can definitely do both in the same, and that's actually not part efficient. Exactly. Yeah, you could. Yeah. So the reason I separate that just because it makes because I had to segment out the starter code part 1, part 2, part 3. So it was easier to say, do this, do this. But yeah, you could absolutely and traditionally for a lot of code, if you combine it together. Yeah. No, that's great. And so now your code's gonna run a bit faster. So here, with that, in one case, all of them. Here, that's not necessarily. Those are not necessarily. No 5. So what you're going to do is so use the one tell you which location. Because we use the like but that also tells you which row. So you're going to that. So those guys will row, but do the connected information. It's not supposed to be. So after you apply the boundary conditions, that breaks the symmetry. You can't have a symmetric polar thickness because then you won't be able to convert. And so it'll be symmetric up until you apply the boundary. Yeah. Yes. You're going to need the Dirichlet. So the Dirichlet edges. So that is a vector that shows you which edges. First of all, which edges you want to find. If you've already used that information, so I'll tell you that you don't need to use that information. And so you shouldn't be modifying well, this is fine. So you can do it 0 for growth, but then that should be the only thing. Yeah, and so this to do here that includes everything that's yes. And so you remember when you have a Dirichlet boundary, you need 0 to grow. You need to put a 1 on the diagonal entry, and then put the Dirichlet value on the book. So you do some of that here. But you should have just kind of one line of code for each. One line for each for those 3 steps. So you have the parts. It's just kind of figuring out which is that one's okay. Yeah. So the Dirichlet value that's what you're going to put in directly to the right hand side. And so just kind of figuring out. I would say you need to delete more stuff in order to paint that. So you have all the pieces there, but not everything. Not everything. Remember, up until up in here, this is when we build the global stiffness matrix, not the forcing vector, we do that first. And so you should do most of those modifications. The visual coordinates, remember, those are based on not the Gauss ones, those are based on physical. Right now, you yeah, and that's key for the that's key for the source of generation. Why is it text? Thanks.
Okay, so on the top one, it's not just one, so it is that we have to do. Everything is one.
Yeah.
It's one, we go over this one. But then this.
Right, so we'll just check in here. So the equation going off is right here. So equation is saying node 1 and node 2 are the boundary.
This one, that's why we choose matrix. It doesn't apply. You just say so
so the assembly is taking care of it. So by this point in the code, you should just modify that because you're already modifying that element of your two. Oh. So you just need to add it to that.
So, for example, like if I turn on this one, that's my question. I don't know. For example, when I select this one, I try to run it.
Yes.
I need to skip this one. This time to have this one, but the rest.
Yeah. So for this right now, you're because it's right. So because this is a like you're you're just adding the value of downloading at this whole. So you're also kind of overwriting what's happening here too, because for this one, it's going to do this plus. And so that says that we don't want to overwrite this.
Yes. So that's why it's because like
Yeah.
it doesn't apply. Then try to figure out then I said, how about
Yeah.
that's why it's just a simple question that whatever Neumann does, so it's a but the rest that's why
This what it should be. Right. Multiply this next is.
so we still apply the equation as we have the triangle like next one. So
Right. So let me check something. So when you add.
I choose this one to indicate like one of them doesn't have, so this is the one.
Yeah. You should add. I'm just gonna check the remember.
One question, so I try to understand this in the new node, right? So I try to go to one of the right? Right, it's only applied instead of this one. They only apply one edge.
Yeah.
They don't apply the rest.
Exactly. Yeah. Just on one edge. Yeah, so whichever one is on the best. So that's what we're testing for. That's what we're seeing, which edge is. That's what I want. Yes, I'm not. Yeah, I got this. Yeah, it should print it out.
Yeah.
Yeah, just we know. So their numbers are.
And what does it mean by total error?
It's so what it does is that it takes the, so here's your solution, here's the reference solution.
Yes.
And so it takes the difference of these two per node, and then it just sums it all up. So 171, that's if you add up all the errors, it's not a it's just the total difference between this solution and this one per node. That's the feedback.
But when I try to run the top 1 and 2, I got the
It's not percent. It's 40, 50, that just means that.
yeah, I know.
Yeah, no, that's fine.
What term, like the lower the better?
Yeah, I mean, lower is better, but there's always going to be some error. It's kind of like what what can happen if you look at that, like, the risk boundary conditions apply on this. Same thing on the first two. So what can happen is that there are that are shared. And so depending on the order of which that you apply for the risk boundary,
Yes.
like this one. And so this one applying here they apply for the so that's 50, that's 25. And so I know for sure some that are here, some that are over here, those big differences. And so depending on how yours is implemented versus how theirs is implemented, that there's going to be those. If you want, one thing that you make is that here, you can change the order of these.
Yes, so that's why like, I changed this one like more. Actually, it doesn't change the percent error. It's only and you see this one, the blues like before like the dark blues like under this one.
Yeah.
So when I change the order of this one, it is it bring on the blue, but the rest is still the same. And the percent doesn't change.
Yeah. I mean, I would look at the figures more so because a lot of that error is influenced just by how it's and so I'd be looking more kind of what's in this area, not around. I mean, if it's over 100, I think it's like 40. It's really tough. Okay, that's all. Let's go back. Is your part? Are you just running a question?
Basically, 1 and 2 is related, but it didn't
Okay, perfect. Awesome.
So, I don't know, can we combine the two parts together because the way I'm writing is different. One part. So can I read this one of them? Because I just see this one, but so this is part 1.
This is this part.
Yeah. So basically I copy out, so because we don't overlap.
Yeah.
So that's why I took out the basically the same.
Yeah.
So
I mean, there's
I
a lot of
think I'm going to do the last one. So it's a variable.
Yeah, of course. Yeah. I mean, the outputs, there's lots of different ways. So that's what I was talking about. But part 2, you can actually combine these two. So
Because like if I leave last one and this. And then this one, the percent is.
Okay.
But I don't overlap because it's done.
Yeah.
Unless, because it's not needed, so that's why. I'll come back to the other one. I don't know why the component function is not.
Yeah, it looks nice. I mean, let me double check the structure of it.
Oh, no. One more question for the distance. I just see this one instead of quadrature is
Correct.
on the last one because because this the function of the thermal conduction is function.
Yeah.
And so that's why when the integral between this one, so when origin half, so I'm going to be able to graph actually this one.
Exactly.
And
Right.
then that's what this one is.
Exactly.
Is it the-
Correct. Yeah. So you have it.
So actually in case the thermal condition is like on, right?
No.
So how do you do this case? When it's on, what's working with the five of zero?
Yeah, so it's always going to be if it's odd, and then we have to get odd.
Yes.
And so if that's the case, then
Yeah.
right, but then you also have a shape.
But the shape function is like constant, it's not like variable.
It is, that's what you're doing. So if you do this function. you also
Oh,
plug
yeah,
in
yeah.
the final. So that would affect, you know, the mineral. But for this one, actually, so this one, the reason we don't do divide by 2, because for the triangle, we're only integrating between, I mean, let's just take this as a second. So we're only integrating. And so that's kind of why. Yeah, exactly. So the reason for we can integrate from minus 1 to 1, the length of this domain is 2. So that's why we divide. If you're the length of the domain, so if we divide by 1,
प्लॉट इसका इशू है मतलब ये सब टी सॉल्व में
okay, these are the issues for. So X1 is the first entry and then eta is the second. So this should be, the 0 should be here and this one.
Yes.
So these two.
Yes.
That might.
Can I change it?
Yes. Oh, so it's 8:20, guys. So we're out of time today. I'll stick around for a while, and so if you still want to talk to me for a bit, but you know we're class is over. So yes. And so Wednesday we'll have the same thing, and so Wednesday we'll have kind of a workshop day, so you guys can bring your codes, and you know I'll help you out. What I'm hoping for is that by the end of this week, you know everyone should hopefully have at least parts 1 and 2 done. If you can have part 3 done by the end of the week, I think you're going to be in great shape. Because then by next week you can be ready. Okay. All right, so thank you everyone for coming today. I'll stick around if you still want to talk to me about your code. But if not, I'll see you guys on Wednesday for our final lecture. That's okay.
इसको सॉल्व किया
The distance is not to be
I saw it. I mean, it's like.
Let me just check something. Yeah.
What should be the range or total?
Let me come back to you. So, yeah.
Oh, you got it. You got the points. I like to.
Yep. Yep.
I think the reference, right, but it's mine, but they don't apply. So that's the. I remember. Yes, okay, I remember. So this is the part that you're saying. So, but I don't blame you on this. So, the tricky part here is that we're moving over this vector here called Nodal. Yes.
And so when you get the connectivity, this, when you're getting the connectivity, it shouldn't be on I2. It should be on Nodal. Because I'll show you. Right, so this is the list of elements that are on that.
Yes.
Right, so 35. And so what we're getting to we're getting that whole like this should be like the entries of that.
Size ratio.
One instead.
Size ratio. Size ratio.
Yeah, because if you do IE, because IE is just going to go from one to one to the length of this. So this is just going to be it's just going to go one. So what you're actually doing is you're applying the boundary condition. 1, 2, 3, 4, 5, 6, 7.
Oh,
Instead of these. Exactly. So why don't you go ahead and make this get closer. So let's give it a try.
Still doesn't-
Yeah. That's better. We're gonna get it closer. Those will get anywhere else. There's one other living solution. There you go.
Oh, yes.
There you go. Looks good.
That's
Looks great. Awesome. So I think the remaining there, I think that's just. Great job.
Thank you.
Yeah.
For that.
Yes, I
Stay
think-
alive.
Yes, I think you're good to go. So I think, go ahead and start
Thank
writing
you.
the report, and then we should be.
Thank you.
Yeah.
And again, I'm so sorry.
Oh, no, it's okay. It's okay.
Yeah.
I was kind of in a,
I'm so sorry.
no, it was,
I understand.
I was, yeah, dealing with something else. So it's not, your fault. Don't
Yeah, I'm
apologize.
so sorry.
But yeah, it looks really good. Great job.
Thank you. Thank you.
Yeah, so there's always going to be some error because if you open up one of the figures right now, so let's look at figure 5 and 6. Yeah, so what happens sometimes, or just one of them. So what happens sometimes that when we apply the Dirichlet boundary conditions, what we have is like we have, this is an edge right here. This is an edge right. We have some nodes that are going to be shared in between those two. And so what can happen sometimes that if you just depending on the order in which you're applying the boundary conditions, you might apply this one first, but then when you apply this one down here, it's going to override it for that node right there. And so you're going to have a difference. So for the reference, it might apply, let's just say, for instance, this is like 50 up here, and this is like 25, right? And so for this node, that node there looks like a share, right? So you might apply 25 there, but then they might apply 50. Yeah, and so I think all the differences are just going to be in these nodes that are shared between these two. So it's really hard to see. Yeah, so that's not a percentage. So what that error is basically I took a node by node difference. So I took those are the two vectors and I just took this difference between them. And that's just whatever. I just added. Yeah. So I would just look at the image. So that's more just for myself for debugging because I was doing some testing too. And I kind of just left it in there by mistake. So I think that's been causing people more panic. It's not a percentage. So that's not a 40% difference.
Whatever they need, like it converts to 0, something like that.
It's possible. It's possible to converge to 0, but you're going to need to play around with the order in which you apply the Dirichlet boundary condition. But you're kind of playing a game there because what I know for sure is that when the way the reference solution works, if you look at this code, like you're applying the boundary condition, you would think that it's applying it in this order, but it's not. It's kind of doing something else internally. And so I haven't quite figured it out. And so I just said, whatever,
Like doing all these things, directing this line of code.
Yes.
Not for the exam, but just for.
Yes. Yeah. Yeah, it was good. Yeah, visual. I mean, go by the visual more so than that. So that. Yeah.
Getting the. Google Matrix and it's all.
Looks like this is a pair of quantities.
It's all.
That's probably your Dirichlet boundary conditions.
Yeah, this.
I think this is what we should do. Oh, okay, I see. So this should be, because you're doing this for this particular element, so this should be I sub E. Because NLM is a fixed value, that's the number of elements, right? Yeah. This is I sub E. Let's see if that's the same. So, yeah, that's fine. So there's no F. Okay, there we go. Yeah, so I think that's really, yeah, that's good. Yeah. Mhm. Yeah. There's some randomness. So when you generate the mesh, we're using basically a mesher inside MATLAB. And so even if you have the same element size here, it's going to produce slightly different meshes just because it's the way meshing works. It honestly depends on some of the random values inside the computer. So, the way meshing works is that I don't have a figure, but basically it takes your domain and it kind of puts points in in semi-random places. And so all the nodes, they're kind of in semi-random places, and then it connects them in semi-random ways too. And so, and that's computer specific. So actually, if you run his code on your computer, you'll probably get the same thing that you got. You run his code on your computer. Because it depends on random, but don't worry about it. So, random. Oh yeah. No, it's because it depends on just random values inside. Yeah, don't worry. Yeah, if you do it on ANSYS too, so on ANSYS you have the same geometry, you mesh it with the same settings, you're going to end up with different. That's just how much. Is that question? Okay. Oh, yes, because Dirichlet value, that's for the edge. So the index here should be for the edge. The edge, not for this one. So if you scroll up a little bit, so instead of my end, it should be I edge.
Because everything on that edge has the same value. And the Lewis rate value, we only connect with that vector is only I always tell people it's great working on complicated because if you run your code and it fails, no one does. You can run the code as many times as you want. Right? It's different if you're designing a rocket because a lot of people will die if you don't design a rocket. But if you do simulations, hey, just run it as many times as you want. Okay. Okay, so I think this is the same issue that. Let's check your. So you need, so it's good that you guys are using IND here, but you need to recompute this for this because you're basically making another loop on the elements. And so you need to recompute IND. And so I wish MATLAB would give an error for this because it should be an error, but you know, something like this, you know, if it's defined earlier, then it's going to just redeem those. Here. Because what you're basically doing is that you're because you're not updating IND1, IND2, IND3, you're taking all your element stiffness matrices and putting them in the same place. So we're going to go ahead and put this here. Okay, and so here's another thing. So you have these entries correct right here, the 1, 1, 1, 2, 1, 3. But this third entry right here, you know, this is for the elements, right? And so you're looping this over the particular elements. And so you want to add in the element stiffness matrix for that particular one. And so you should use the loop index here, I said.
Thanks.
Yeah. Okay. Does that make sense? Because you know, IND1, IND2, IND3, those are the nodal indices, but you want to add the entries. You want to add the entries for the element indices. Because this element stiffness matrix belongs to that, so you should use the element.
Fixes the same.
We'll see. So this error is happening basically because you're not getting a converged solution. So basically the simulation is blowing up, and that's mostly because the global and the element stiffness matrix, the global and the global stiffness matrix and the global forcing vector are not properly constructed right now. Okay, so I'll prove it tomorrow morning.
I have a question about the bonus part 4. So, but in that one you mentioned about like loop for one loop include everything.
Yeah.
But I don't think it's include the Neumann condition because like we didn't call any element.
Yeah, so the Neumann boundary condition you can accept. That's fine.
So it's only
So it's
like
basically
by part 1 and 2.
part 1, part 2, and the assembly. So all of that can be done.
The assembly
One.
is in one loop, but
Yes.
the Neumann is separate.
That can, yeah, that's it.
Cool, I think I got it.
Okay.
Thank you.
Yep.
Thank you. Thank you so much.
Great, awesome. Okay, so that is a little bit high. So the error, I should send an email about it. So I think people have been thinking that's like a percentage error. It's not a percentage error, don't worry. So what that is basically is that for what I did was like, you know, these two are the exact same meshes. And so what I did basically was that I looped over every single node and I took the difference between your computed solution and the reference solution. And then I just added those up all together. And so that is just kind of the total. That's why I call it total error, because it's something like that. And so if you want to measure it like average error, you would take this and you would divide it by the number of nodes that you have. So that's the average error per node in temperature. So this is part. Oh, so this is parts 1 and 2. So you have both. So you have so this is the thermal generation function. Right? This is starter code 1. I don't think I added thermal generation function to this one. Yeah, so this reference solution is not going to have that the thermal generation function. And so you would actually copy and paste this code in part 2 because you have this SU, this SU step. But for now, I'm just going to go ahead and just comment this out. So what people have been getting usually for this part is like an error of 40. Yeah, so you kind of did parts 1 and part 2 together. Okay, that's more. Okay, so if you take your thermal generation code and put that in part 2, that's going to that's going to help you there too. So you kind of did parts 1 and part 2, but this is just part 1. Where part 1 is just the element stiffness matrix and the ratio. Which was good. Yep.
And that brings me to
Yeah.
I sort of pretty much filled in what I could since I was still on. So I sort of saw so it has this part which
Yep. Yep. Yeah, so you have to be careful not to do this twice because you did it all in the same loop. This is kind of what I envisioned for this loop right here. So I have it separate just because it makes it a little bit more clear to the program. But you can actually do them both together in the same loop, which is what you did. So you definitely don't want to repeat it because you don't want to do it twice. Okay, so you can go ahead and delete this loop and just do it all in one. This entire loop right here because if you scroll up a little bit. Yeah, and so here you're already doing so part 2 is basically to have an element forcing vector. Part 1 we actually don't need an element forcing vector. Part 2 is to include that part. So if you're doing that all in this loop up here, you don't need this other loop right here because you're doing it all together. Yeah. That last one as well. You can go ahead and and then you're gonna have to apply the same changes with ISOs and stuff like that. Yeah, so the way I kind of envisioned it was that you would have this first loop without the SG stuff, and you'd have the same loop again with the SG stuff. But if you do them both in the same, because it's the same loop, so it's IE with 1 over the elements, and so you can do them both in the same loop here. So that's okay. And so that's like that. So that's just a little bit less code. So, yeah. Yep.
Matrix is not supposed to be the same all the way.
It actually might. So I was actually looking at the percent intersection. Close to the same.
I'm not sure what to do.
Okay, so we'll take an error.
So I do the notes. And then I get the coordinates on those. That's will be in.
Yep.
And then this makes sense in my head. I'm not sure if it's right, but like at no.
Yeah. So it is right. And so you have to read it. Because what it's doing is that it's this N1, N2, N3 should update for each one. That's different.
Yeah.
What's happening there? It's taking the values for N1, N2, for the final entry. You don't want that. You basically want
So that means
okay, so that one's besides that one's good. Yep. Yeah, guys. You don't have any tests. debugging code is.
I struggle so much with that one.
You're doing good though. You're off to a good start. Yeah. So usually what this error is that you're trying to access like a vector. And you're accessing. Ah, okay, okay. I see. So what you're doing right here, you're kind of redefining the value. You just have to call this because because the equal sign here basically means assignment. And so you say Dirichlet n is equal to Dirichlet n is at I edge. Then you're resetting the value of Dirichlet n to a single. Okay. Yeah, okay. So yeah, so Dirichlet n you can see is reset the value. So you can see the okay, so that's right. Oh, okay. Okay. So remember the Dirichlet values. This is a value that belongs to the edge. And so we're going to replace this right here with my edge because this IN is looking over all the edges, which is a lot. So this Dirichlet values vector only has 8 degrees. IN could be something really big because it's more than 8 nodes on the edge. And this is going to go. That's also going to go like that. Yes. So there. So don't worry about the total error all that much. I mean, it isn't enough to tell people not to worry about it. But basically, the way I computed this was I basically took the difference node per node between the two entries. That's just the total. So you're gonna have some error here just because of the way the Dirichlet gap recognition is implemented. Yeah, I can explain it a bit better next time, but I'm kind of running out of fumes right now. I'm not doing it, but in other words, don't worry about it. So you're basically all good for part one of this code. All right. Thank you. Yeah. Yeah, I'll explain that more on Wednesday. One final question. Really helps.
I don't know what
You need to have a oh, interesting. Okay. So this F element right here, this is going to be just particular for this element. So F element is supposed to be a 3 by n. So what we need to add here is you should add it for so you should have a colon here. And then for 5, just like right. Because remember, each element is going to have a different element fitness or a different element force. So you need to save each one. Because if you have just that element here, it's going to overwrite the packet. So you want to make sure you save. Looks like it made it worse, but don't worry. It's better, trust me. I think it's still not 100%. So there might be a small error somewhere. Sorry, that's the elements. It's kind of an advanced, there you go. That's what I'm doing. Yeah, so this is kind of a pretty advanced method. You're basically, this is the back end of what's on in the ANSYS system. Kind of coding the beginnings of an ANSYS software. But it was good. So that's part one, part two.
All right.
All right, I gotta go because I
Thank
started.
you.